Swayam Prabha. Digital India. Educated India.
So good morning and welcome back to NPTEL lecture series on classics in total synthesis. So today we will talk about a natural product which is highly substituted anthraquinone as a core structure. So that natural product is called Vineomycinone B2 methyl ester. Actually these vineomycins have this common dihydroxy anthraquinone as the core structure. There are quite a few vineomycins, but today what we are going to do is we are going to talk about a couple of total syntheses of this vineomycinone methyl esters. You can see this is a methyl ester, so that's why it is called vineomycinone methyl ester. So all the vineomycins show exceptional activity against gram positive bacteria and also against some tumors in mice. The two syntheses which we are going to talk about today are from Danishefsky's group and Tius group. Danishefsky synthesis used a very interesting heterodeal reaction to construct this dihydropyran ring, and they also used a Claisen rearrangement to introduce the side chain on the right hand side. In addition, they also used a Diels-Hall reaction to construct the anthraquinone moiety. Let us see how Danishefsky's group used these key reactions to complete the total synthesis of vineomycinine B2 methyl ester. First, let us look at the retrosynthesis. So they made this vineomycinine methyl ester from this methyl ketone using a Reformatsky type reaction. So one can easily see this CH2CO2Me group can be added to this methyl ketone via Reformatsky reaction. And this methyl ketone, if you look at carefully, on the left hand side, that is this dihydropyran. Okay. So this was converted into the dihydroxyl group here using hydroboration. Okay, hydroboration oxidation. Already there is a enol TMS. One more hydroxyl group was introduced using hydroboration oxidation. And as I mentioned, this particular dihydropyran unit was made through heterodeal reaction. Okay, you start with that aldehyde and then you do a Diels-Hall reaction with Danishefsky's diene, you get corresponding dihydropyran. Okay. And this aldehyde can be obtained from this allyl group by isomerization of this double bond. Okay. Once you isomerize the double bond, it goes to the internal alkene, which upon ozonolysis will give corresponding aldehyde. And if you look at this compound, you can see here this also upon Claisen rearrangement followed by ozonolysis, you can get this methyl ketone. Okay, it's a 3-4 steps involved in this reaction, in this particular transformation. And this can be obtained again. So this is the diene. Okay, this is the diene, and this substituted naphthaquinone is the dienophile. They can undergo an intermolecular Diels-Hall reaction and followed by aromatization to give this substituted anthraquinone. Okay, and that can be obtained from commercially available natural product called juglone. Okay, now let us see how the forward synthesis took place. So he started with again commercially available methyl crotonate. Now if you treat with LDA, if you treat with LDA, what will happen? This CH2, this will be picked up. LDA will pick up this proton and it can generate anion here, and that place one can quench with allyl bromide. Okay. So it picks up the gamma proton and then quenching with allyl bromide at alpha position. So that will give this alpha, beta, gamma. So beta, gamma unsaturated ester. This ester, as you can see, this proton is still acidic, isn't it? So you can generate anion and quench with TMS chloride. So that will give you the corresponding starting diene which is required for Diels-Hall reaction with juglone. Okay. So once this is made, then the juglone which is required for the Diels-Hall reaction was deprotonated, that phenolic hydroxyl group was deprotonated and quenched with this allyl iodide to get the precursor not only for the Diels-Hall reaction, because as you can see this is the quinone moiety which can undergo Diels-Hall reaction, and here this allyl ether which can undergo the intramolecular Claisen rearrangement. The other starting material, that is Danishefsky's diene, was prepared from this enone using LDA and TMS chloride. Now let us see how the Diels-Hall reaction worked. So first he started with this diene which was prepared from methyl crotonate, and Diels-Hall reaction with 2,5-dichlorobenzoquinone. 2,5-dichlorobenzoquinone gave this intermediate. Of course this is unstable, so it was not isolated. It underwent elimination of HCl, also methanol, to give this hydroxy naphthoquinone. Okay. Then the free hydroxyl was methylated. Okay, the free hydroxyl was methylated, followed by isomerization of the double bond. That allyl group was isomerized using Wilkinson catalyst. Then the next Diels-Hall reaction was done on this chloro-naphthoquinone. Okay. So that gave this intermediate which was subsequently aromatized to give this compound. Okay. Now you can see here you have the double bond which can be ozonized to get aldehyde, and here also you can get this ketone. Okay. So this is one way they prepared the key androquinone. They also used another method to prepare the same intermediate, where they started from juglone, which I already mentioned, and they allylated with this allyl bromide, substituted allyl bromide. Then Diels-Hall reaction with this diene followed by aromatization, he could get this compound. Now you methylate this phenolic hydroxyl group, and what you need is to isomerize the double bond to internal alkene. So that was done again with rhodium chloride. You can isolate the double bond, so you can isomerize the double bond, and then when you heat it at 200 degrees, then the Claisen rearrangement takes place. So that migrates the allyl group to ortho position. Then you can methylate this free phenolic hydroxyl group as well, and followed by ozonolysis you get this side ketone. This upon ozonolysis you will get ketone, and this side you will get aldehyde. Okay, this is the highly substituted androquinone moiety, which is the core unit of Vineomycinone P2. So what needs to be done is one has to do a hetero-Diels-Hall reaction on the aldehyde on the left hand side, and then one has to add the CH2COTMe through Reformatsky type reaction. Okay. So he carried out the hetero-Diels-Hall reaction with this diene, followed by isolation. When he did the Diels-Hall reaction with this diene, he could get this dihydrofuran, which upon hydroboration, followed by oxidation with hydrogen peroxide and sodium hydroxide, you can see the required diol was obtained. Okay. So, now the diol is there. Next is to carry out the corresponding Grignard reagent. So, the Grignard reagent did not work. Actually, original plan was to carry out Reformatsky reaction. So, here he tried this the alpha bromo methyl acetate and formed the Grignard, and this reaction did not go. So, instead, so what he did, so they removed both methoxy group. Okay, they removed both methoxy group with BBr3. With BBr3, both methoxy were removed. Then from methyl acetate, this proton was deprotonated using lithium hexamethyl disalicide. That lithium derivative was added to the ketone. Okay. And of course, to facilitate that, magnesium bromide diethyl ether also was added. So, now this reaction worked very well, and that was converted into corresponding Vineomycinone B2 methyl ester after removing the TMS. Okay. So, that is how this total synthesis was accomplished, and it started from commercially available natural product called Juglone, and it involved heterodeal reaction, normal deal reaction, Claisen rearrangement as key reactions to synthesize this compound. Overall, he took about 11 longest linear steps with a yield of 9%. Okay. So, 9% overall yield is a very good strategy. And now let us see the second total synthesis, which is chiral one, and this was reported by Marcus Tius. So, the left hand side glycol part, he started from D-glucol. Okay. So, D-glucol was the key starting material to introduce the chiral center. Okay. And according to him, this Vineomycinone can be easily disconnected into 3 fragments. So, this is one fragment, and then middle, the dihydroxyandroquinone is the second fragment, and the third fragment comes from this intermediate. Okay, these are the 3 fragments you could easily disconnect, very logical. Now, let us see how he made these 3 fragments and then combined all. He started with beta hydroxy carboxylic acid. This, upon treatment with pyvalaldehyde, the presence of acid, it gave this protected compound. Okay. Now, he wanted to introduce a double bond here. So, that was done first bromination followed by elimination. He got the double bond, and still you can see there is one stereo center. Then the allelic bromination was carried out with NBS under photochemical condition. So, one side chain is already prepared. The second side chain is started with D-glucol. Okay. The triacetate was hydrolyzed to get the triol. Then the primary alcohol was methylated. Then both the secondary alcohols were acetylated. Okay. The mesylate, upon treatment with lithium iodide, the mesylate is converted into the corresponding iodide. Now, upon treatment with LiH, so this iodide will be displaced by hydride, and ester also will be reductively removed. So, you basically what you have done is from the D-glucol, the CH2OH is converted into CH3. Okay. And both the hydroxyl groups were protected as TBS ethers. Then treatment with butyl lithium, tertiary butyl lithium, one can generate anion here, and that was exchanged with zinc for the Negishi type coupling. Okay. Then for the middle portion, this is a commercially available dihydroxyandroquinone. Take this and protect both hydroxyl groups as MOM ether. Okay. Then reduce these 2 ketones, reduce these 2 ketones with sodium borohydride isopropanol completely to get the corresponding aromatic one. Okay. From androquinone, that is dihydroxyandroquinone, what we have done is dihydroxy protected anthracene. Okay. So, then it is a symmetrical compound. So, treatment with tertiary lithium, either it can generate here or here, does not matter, both are same. Then exchange it with tributyl tin chloride. Okay. So, then you exchange that with iodine. Okay. The tributyl tin can be easily exchanged with iodine by treatment with iodine. So, this side you have iodine and that side you have zinc. So, then do the key Negishi coupling to get or introduce the CC bond. Okay. Then this sodium cyanoborohydride will reduce this enol ether. Okay. The sodium cyanoborohydride will reduce the enol ether stereoselectively to get exact tetrahydropyran unit with all stereo centers fixed. Now, what is left? As you know, you have to introduce a tin group here and then attach the CH2 side chain. Okay. So, first introduce the tin by treating with N-butyl lithium and then quenching with tributyl tin chloride, and this upon coupling again, this time it is like still a coupling. So, that gives the corresponding side right hand side chain. Okay. So, if you look at this, what is missing is a methyl group at this carbon, but you have enone. So, one can easily introduce a methyl group using Gilman's reagent. So, that is what he did, and that methyl 1,4 addition took place highly stereoselectively because of the presence of the tertiary butyl group. Okay. Then what needs to be done? If you look at this middle ring of this anthracene, in the natural product it is anthraquinone. That means this diene should be oxidized to diketone. So, that was done to get the corresponding di-substituted anthraquinone. Okay. So, what is left? You have to remove this tertiary butyl group, you have to remove both MOMs and you have to remove both TBS group. So, if you treat with HCl, so this will remove and then you also will get methyl ester, MOM group will go and also TBS group will go. So, it is a complete global deprotection followed by esterification, all were done in one step to complete the asymmetric total synthesis of Vineomycinone B2. So, in summary, Marcus Tius and his co-workers completed the total synthesis of Vineomycinone B2 in early 90s, and they started with the commercially available 1,8-dihydroxy anthraquinone and also D-glucol on the left side, and the other side they started with beta-hydroxy carboxylic acid, which is also commercially available. Okay. There are two key reactions which they used. One, Negishi coupling on the left hand side and Stille coupling on the right hand side. And the last to introduce a chiral center on the right hand side chain, they used Gilman reagent to introduce the quaternary center. Okay. So, they took about 11 steps and overall yield was 4.6%. Considering the complexity of the molecule and also the first asymmetric total synthesis, this is a significant achievement. Okay. So, I will stop here and then we will continue our discussion with one more natural product and complete the syllabus of this particular course. So, we will discuss tomorrow about the total synthesis of another complex natural product called xaragosic acid. Okay. Until then, see you. Thank you. Bye.